Hello, this is Professional Coding with Vladimir and we're discussing essential algorithms. And today we're going to discuss three-pointer technique for reversing a linked list. It's a somewhat legendary algorithm. There are many ways to reverse a linked list, multiple ways at least. And a lot of people are talking about this technique. It's not super hard to learn, but if you don't know it, I think it will be a problem to come up with the appropriate logic, because three pointers it's hard to tackle them all at once if you're not prepared. So we'll understand other approaches, we'll estimate their runtime space complexity, and we'll compare it with the approach that I advise you to master. And this approach will be useful for different tasks that are related to linked list. Out of linked list topic, I think it's not that important, but still, you will be expected to know this algorithm and to use it. So I can also recommend to learn it by heart, or at least it's always better to understand it so you can recreate it from the top of your mind every time you encounter that. Every time after a year I forget how to do it, but after like 5 minutes of sitting and drawing the task, I can redo it once again. So I hope it will be helpful. Linked list is an interesting data structure. Sometimes it's used on interviews, not every time, but sometimes it's used. So it's better to know at least basic stuff, how to work with them. And reversing a linked list will definitely show the principles of working with a linked list. So let's start. Let's first recap the task. So we have a linked list of length n. In our example, it will be length 5 and nodes from 1 to 5. And each node, as you might remember from the linked list data structure, has a reference to the next node. So for the first one, there is a reference next, which points to the second node, and so on and so on. And in the very beginning, we have access only to the first node, which is called the root of the linked list. What we want to get in the end is exactly this kind of linked list. So it starts with 5, it's a root, and then the next goes to 4, so it's vice versa, and the previous root now points to null, which means it's the last element that's there in the list. So it doesn't seem very easy to convert this structure to this one, because we may see that this part is the same. I mean, it changed the direction, but the null goes from here to here, so nothing points at 5 from that moment, and 5 becomes a root. So it's not that obvious how to do that. We have some naive ways to do that. First way to do that is to convert our linked list to an array. And it's a very widespread solution. So a lot of people without special knowledge of linked lists will attempt to do that in that way, and it's perfectly fine, I think, unless we want a better performance, better runtime or space complexity. So let's see how it's done. First of all, you have a list, you traverse it, and you create an array one by one. You just push elements to an array. Then you use any method to reverse an array. For example, I prefer 2 pointers, but that can be any method to reverse an array. And then you are traversing an array once again, and you are recreating the list that you want, where 5 will be at the first place, 4 at the second, and so on. So for that, we'll have a time complexity big O of n, because we need to iterate through all the elements, and not once, but a couple of times. And we'll have to allocate an additional space for that. So we'll have a new array, we'll have a new linked list, and that will be big O of n for space. Another naive way is to pick the last element one by one. So every time we're going through the entire linked list, and when we face the last element, we can see that it's last if the next element is null, and we have access both to the next element and the current one. So when we face the last element, we just take it from here and we add it to our linked list, a new one, a reversed one. that we will prepare beforehand. So it will be n iterations, and every time you should go through n elements, then n minus 1, then n minus 2, and so on, and it will give a complexity n squared. But it won't require any space, any additional space. Maybe n less the result itself. So it's good to mention that you have a linked list that will have will consume space. So I would say that it's still big O of 1 because we are reducing our current array. I think that that's a correct assumption. So we are removing elements from our given array, and we are adding them into our new array. So basically the entire number of nodes will remain the same. So yeah, big O of 1 constant space is a good estimation for that. But of course, if it's n squared, it's a very bad runtime complexity. Okay, then there is a question. Can we optimize it? Can we pick another algorithm to combine like benefits of point 1 and point 2, to have time big O of n and to have a constant space? That sounds almost like an impossible task if you don't know how to handle it beforehand. And here comes our solution. So let's understand how to solve it. Three pointers technique. It will take our linked list and reverse it in place with n runtime complexity big O of n and constant big O of 1 space complexity. And that sounds insane, but in fact it's quite easy when you start to understand it. So we'll have three pointers, as that's the name of the method. And we'll have a current pointer that will point to our root when we just start. We'll prepare a previous pref pointer which will point at null. And that will be our new end of our linked list, but you'll see how it will happen later on. And we'll have a temp variable which is not created yet, but I'll use it during every iteration. So let's start our iteration. So we have current, and what we want to do, we want to save this current next element. So the element that goes after the current one. And that element is 2. So for that, we need to assign current next to our temp variable. So we use this temp variable to remember this node. Now we can safely change this car next link so it points to our null, or better say to pref variable. After that, we can safely move pref. Pref will now equal our current variable. That's how we prepare for the next iteration. And then we safely move car so it equals temp. That's why we saved our node in temp, not to lose it, because in the linked list, if you remove this next reference, you will lose the next value that was there. But we saved it beforehand to the temp variable. So now current will be equal to temp, or the second node. And that's one iteration. Now we just repeat it until current is not null. That's pretty important. And let's do it a couple more times. Once again, we are saving car next in the temp variable, so we can return to that later on. Now we can safely change the link, so now it references to the pref, which is the first node. Now we assign current to pref, so pref will equal to car, and car will be changed to temp. So it will be our third node. And we start a new iteration. We save this node into temp. It will be car next. So temp equals car next. And then we'll choose, we'll change the reference to our previous element, to pref. Now we'll update the pref, so it equals car. Now we'll update car, so it equals temp. And the new iteration starts. We're saving the next element into temp. We're changing the reference to that element, so it points to previous element. And we update the pref, so it equals the current element. We update the current, so it equals temp. And we start our last iteration. We go to null, so we save this. We don't need that, but the algorithm will do it. Then what we're gonna do, we're gonna change the reference. Now it's pointing to 4, or to pref, and we update pref. Now it equals car, and now we update the car, which equals temp. And the next iteration won't happen because we know if car is null, then we stop. So it's a while loop that will stop. But now we need to return the new root of this reversed linked list. And the new root is in 5, right? But current is already at null, and current doesn't know how to return back because there are no references between null and the previous node. So what can we do here? And the answer is very, very interesting. We can just use the pref. We save this link in pref, and pref is now our new root. So we will just return pref. Now let's do a simple edge case where we have only one element. Root is just one node that points to null. Will it work the same way? Because if the root is null, it's very easy to handle. The while loop will just shut down immediately, so we won't have anything. We'll return previous element that it will be null at that point. But what about one element? Will it work? Yes, it will. So let's follow the same logic. We have current, we have pref, and when we start, we say we need to save the next element so we can address it later on. So we say that car next, or temp equals car next, and we change this reference. We change it so car next equals pref. And now we move pref, pref now equals current, and current equals temp, as we saw before many times. And the next iteration won't start because while loop will see that current is null. And we will return pref because it's our new root, the same way we did before. And that will be exactly the correct answer, because now it will be node 1 still pointing at null. It will be kind of another null, but for us it doesn't matter, it's still null. So even this edge case works perfectly fine. We don't need to introduce another rule that, for example, we have only one element and the second one is null, then we should do something else. No, it just works out of the box. Let's code our beautiful algorithm. We'll start with class of the node. It will be a simple class with one constructor and a couple of properties. It will be value and it will be reference to the next property, which by default will be null. This val equals val, and next equals next. Now let's do the reverse function. It will have only one parameter. It's called root node, or root. And we need to create pointer that we discussed. So first of all, it will be our current pointer that will be root node at first. We'll also have the previous pointer, which will be null, as we described. And we'll have a while loop that will last till car is there. So I'll just have a short form of this clause. Okay, what we are going to do next is the best part of the algorithm and the hardest one. So first of all, we'll create a temp variable where we'll store current next, as we discussed before. Next, what we're gonna do, we're gonna have we're going to change this next to our previous value. Then we want our previous value to be the current node. And then our current node must become temp. And that's it. In the end, we're returning prep. Let's test that. For that, I prepared some code because it takes some time. We'll have a couple of lines. First of all, our root node, it will have the entire list. So it will be a new node with value 1 with another node inside of it. That's a pretty convenient way to write short linked lists. Same way for this one. It will also have two parameters, and this one and the fourth one. It became really big. Okay, so we have this thing, and we have JSON stringify, so node will show us the entire object instead of cutting that or reducing it to a couple of lines. So there will be console log stringify of the initial node. I don't think we need it because we already see it here. What we really need is the reverse node. Let's do it, let's launch it. So here we can see that we start now with value number 5, next one will be 4, next one will be 3, and so on till the value 1, and the next one for 1 will be null. So that's what we expect. So it's working. So I think that we covered this 3 points technique for reversing a linked list. It's one of the things you better know before your interview. It can help you in different types that are related to specifically to linked lists. And yeah, please stay tuned, subscribe if you found it important or interesting. And I think we'll have more essential data structure in near future. I think it will be interesting.